All right, so in this video we're going to go over molarity and dilutions. So still a little review. You might learn something new, maybe not. Okay, so molarity, the moles of a solute in every liter of a solution. It's also known as the concentration. So if it asks you to find the concentration, find the molarity. It's the moles per liter. The more stuff is in the solution, the more concentrated the solution is. So if you got more stuff dissolved into it, the higher the concentration, right? So if you look at my terrible little drawing here, if each purple dot represents 1 mole of the solute, what is the concentration of the solution? So remember, guys, side note, a solution is made from a solute being dissolved in a solvent. The solution is the combination of both of those things, all right? So if we count the number of dots here, we've got 1, 2, 3, 4, 5, 6, 7, 8. So that means there's 8 moles of solute in 1 liter, right? Because it's filled up to 1 liter. So that means it's an 8 molar solution, right? So that would be the concentration of this. So molarity, whenever you see this capital M, it can be written like this, and then we can also use it as a conversion factor, just like molar mass, where we have for every 1 liter there's 8 moles. All right, so you can write it like that, or you can write it like that one. All right, so keep that in mind while we go through this video, because that will really help you if you're not plugging it into the molarity equation every single time to do calculations. All right, so if we want to make a solution of a particular concentration, it says, how would you prepare 500 milliliters of a 0.5 molar solution of sodium carbonate from solid sodium carbonate? All right, so most questions will only ask you to do the calculations. They're never going to ask you to draw it. Now, they might ask you to describe how to make it. So you should really try to picture how this would look in the lab. So my my little balance here, I'm very proud of this balance. It took me forever to make it. All right, so we have 26.5 grams of sodium carbonate. It's measured out. So if you were to do the calculations, all right, let's go ahead and go through that really fast. All right, up here. So if I have 500 milliliters, right, and I have 0.5 molar solution, you should always start with the one that doesn't have a denominator, the unit that doesn't have a denominator. And since molarity is moles per liter, we're not going to start with that one, so we'll start with the other one. So I have 500 milliliters, and there's 1,000 milliliters in 1 liter. Guys, you need to know that, okay? And it's going to be 0.50 moles per liter. Right, so I'm at moles and I want grams. So to go from moles to grams, I use molar mass. So 1 mole of sodium carbonate, and I'm not going to calculate these anymore in the videos. I'm just going to write down the molar mass, but guys, you need to know how that's found. So it's 106 grams per mole, and we end up getting 26.5 grams. So we would weigh out 26.5 grams of the solid sodium carbonate here, and then we would put it into this volumetric flask, right? So it would go down into the bottom of this volumetric flask, and then we would fill it up to the line, right, to the 500 milliliter line with deionized water. And then make sure it all gets dissolved, and then that solution would have a concentration of 0.5 molar, right? So why would we use a volumetric flask instead of a graduated cylinder? This is one of those questions that kind of comes up on the AP test in some of the open response parts, the free response parts. And basically it's because it's more accurate, right? The sodium carbonate, when we put it in this flask, it's going to take up space. So we can't just add 500 milliliters of water. It's actually going to be less than that because some of that sodium carbonate is down here taking up space. So if we fill it up to this line, we know that that solution, the total solution, is 500 milliliters. Because remember, the molarity equation, right, is moles of the solute per total liter of the total solution. And the solution is all of it. It's the solvent and the solute. So it's not just one of them. All right. Okay, so tips performing molarity calculations using dimensional analysis. So we always start with a number that does not have a denominator in the unit. Okay, so you don't ever start with molarity. So it says, what is the volume in milliliters of a 0.035 molar solution of sodium hydroxide that would contain 0.25 grams of sodium hydroxide? So I'm not going to start with molarity because that's moles per liter. I'm going to start with grams. So I have 0.25 grams of sodium hydroxide, and I want to get to liters, right? So I know I have to use this, but first, because I have grams, I have to use the molar mass. And the molar mass of that is 40. And I put grams on the bottom so that it cancels out. So there's 40 grams of sodium hydroxide in 1 mole of sodium hydroxide. Now I can use the molarity, right? And so what this says right here is it says that there's 0.035 moles of sodium hydroxide in 1 liter of sodium hydroxide. So I'm going to put that 0.035 moles of sodium hydroxide in the bottom and put 1 liter of solution in the top. Well, there's basically my answer because 1 liter is 1,000 milliliters. So if I perform this calculation, 0.25 divided by 40 divided by 0.035 times 1,000, I get 178 milliliters. Now I have 2 sig figs, so that would be 180 milliliters of solution. All right, number 2, how many grams of HCl would be required to prepare 50 milliliters of a 2.50 times 10 to the negative third molar solution of HCl? So this is a very weak solution, right? And I'm not going to start with molarity. I'm going to start with milliliters. 50 milliliters, and there's 1,000 milliliters in 1 liter. Now I can introduce molarity, and so this is let me write this down here. 2.50 times 10 to the negative third moles per liter, right? So I'm going to put the moles on top. And that's of HCl. And then the molar mass of that is 36.45 or 46 grams per mole of HCl. And that's going to give me 0.004557. Okay, now this only has one significant figure, so I could write this 5 times 10 to the negative third, or just 0.005. All right, let's see what else we got here. All right, so what is the concentration of the resulting solution if you mix together 100 milliliters of 0.5 molar solution of KOH and 225 milliliters of 1.63 molar KOH? How do you find molarity? You find molarity by taking the moles of the solute, which would be KOH, and you divide it by the liters of the solution, right? So first I have to find the total moles. So I've got 100 milliliters of 0.5 molar solution. So that's going to be 100 milliliters divided by 1,000 to turn it into liters. And then I've got 0.5 moles in every liter. So liters cancels, milliliter cancels, and I end up getting 0.05. Right? So that was the first one. And I'm going to do the same thing for the second one. So I've got 225 milliliters divided by 1,000. And you don't always have to write that out. I will stop doing that eventually. okay, times 1.63 moles in every liter. And you end up getting 0.36675. So if we add those together, we get 0.41675. So that's my solute. Then I need to take that and I have to divide it by my total volume. So what is my total volume? Well, I've taken 100 milliliters and I've added 225 milliliters. So total I have 325 milliliters, right? So I'm going to take 0.41675 moles and divide it by my total liters. So I've got 100 milliliters plus 225 milliliters. That's 325 milliliters. And if I divide that by 1,000, I get 0.325 liters. So that's going to be 1.28. Now, a good way to check this, if we add a weak solution to a stronger solution, so we added 100 milliliters of weaker solution to the stronger 1.63 solution, it should be between those two numbers. All right. Number 2, what is the concentration of sodium ions after mixing together 55 milliliters of 0.35 molar sodium carbonate with 37 milliliters of 2.32 molar sodium chloride? So this one is a little bit different, all right, because we're looking for the sodium ions. So I'm going to first find the concentration of sodium ions, or the moles of sodium ions in this one, and the moles of sodium ions in this one. So if I take 55 milliliters and I divide by 1,000, I get 0.055 liters. And why am I starting with that one? Because molarity has liters in the denominator. Okay. And then for every single mole of sodium carbonate, I have 2 moles of sodium ions, right? Because there's 2 of them. So that is going to give me 0.0385. of the sodium ion. And then I'm going to do the same thing for the other solution. 2.32 moles of sodium chloride for every single liter. And this one, there's only 1 sodium in there, so it's going to be the exact number, 0.08584. And then we're going to add both of those together. So the total sodium moles is 0.12434. And then we're going to divide that by the total volume, which is going to be 92 milliliters. If we take 55 plus 37, that gives you 92. So that's 0.092 liters. So I'm going to divide by 0.092 liters, and I end up getting 1.35 molar. And that's for the sodium ions in the solution. All right, now I'm going to do the same thing for the other ions, but it's not going to be nearly as difficult, right? So the chloride, we're going to have the same number of moles from that second solution, because there's 1 chloride there, right? And that's going to be in 0.092 liters. And so I'm going to get 0.93. Carbonate is a little bit different. So for carbonate, because there's only 1 carbonate here, right? There's only 1 carbonate in that. We don't have to multiply by this 2 to get there. We'd actually multiply 1 mole of this has 1 mole of carbonate. So it would just be half of this number right here. right? So if you took 0.055 and multiplied it by 0.35, this and this, you would get the number of moles of carbonate, which is 0.01925. And we're going to divide that by 0.092 because that's the volume of the solution now. Whoops. And so that's going to be 0.29, 0.209, or 0.21. All right, so solution, dilutions. Here's the equation up here, right? M1V1 is equal to M2V2. Anytime you're doing a dilution, you're adding solvent, and so it's getting more diluted. So if you look here at this picture, right here, it's more diluted down here. So it has less solute per solvent, right? So we could take this and add a little bit to this cup and then add some water or whatever the solvent is and then dilute it and dilute it and dilute it, right? So that's all a dilution is, all right? And then this equation is used. You just have to make sure that when it says something like right here, where it says 1,750 milliliters of 0.3 molar, that those two are both placed on the same side. All right, you can't put this 12 with this volume because it's not of that, because of in math means to multiply. So these two have to be multiplied together. All right, so how much of a 12 molar hydrochloric acid would be needed to produce 1,750 milliliters of 0.3 molar? All right, so I'm going to call 12 molar V1, or M1, I'm sorry. And then we're looking for V1, and that's going to be set equal to 0.30 molar, and my V2 is 1,750 milliliters. And your volume here can be, your volumes can always be in milliliters, they can be in deciliters, they can be in liters, they can be in cubic centimeters. It doesn't matter as long as they're the same unit on both sides. All right, so I'm going to divide both sides by 12 molar. Molarity cancels out, and I end up getting 43.75 milliliters. So I'm going to take 43.75 milliliters of this 12 molar solution, and I'm going to put it in a flask, and then I have to dilute it to 1,750. So that means I'm adding the difference in water. So I'm going to subtract 43.75 from that, and that would give me 1,706.25, if you want to get technical, milliliters of water added. So the next problem is, what is the concentration of the resulting KMnO4 solution when 287 milliliters of a 1.5 molar KMnO4 solution is diluted to a total volume of 600 milliliters? So I'm going to say 287 is my V1 and 1.5 is my M1. So 1.50 molar, 287 milliliters V1, and then I'm looking for M2. I want to know what my new concentration would be, and this is total volume, so it's all good. I can just stick that right in here. Oops. Then I'm going to divide both sides by 600. And M2 ends up being 0.7175 molar. All right, that's it, guys. This is the video. My dog is trying to break into the bedroom where I'm recording. Are you happy, Bowser? You totally interrupted it.